So everyone, I'd like to welcome Meenakshi Nair. Meenakshi is a ninth grader at Mission San Jose High School. Thank you. And so she is going to be speaking about her research project on identifying planetary nebula. So I think Dr. Oza is still here, so that would be a good opportunity for you to tell him what you've done.
Yeah, for sure. Okay, so I'm going to get started. Hello, everyone. My name is Meenakshi, and I'm an upcoming sophomore at Mission San Jose High School. Today, I will be presenting my project, a novel deep learning and machine learning hybrid technique for automatic classification of nebulae. The night sky is truly a marvelous sight. There lies a vast universe beyond Earth that scientists continue to learn more about every day. The Hubble telescope released in 1990, and since then, 1.3 million observations have been taken. There are around 20,000 nebulae in the Milky Way galaxy, but humans have only been able to catalog around 1,800 of them. Our modern telescopes are able to automatically explore space and discover new astronomical bodies. However, their classification is a human skill, which ultimately takes time and is subject to human error. The goal of my research was to make the classification of nebulae automated, faster, and more accurate, and along the way to discover the best AI model and best techniques to increase the model accuracy. So classifying nebulae brings us one step closer to finding the chemical composition of a nebulae, and this is extremely essential to help us understand the material of the original star. In addition, the presence of certain elements can help us learn more about our universe. For example, the Orion Nebula recently helped scientists learn about the abundance and distribution of phosphorus in our universe. So there are 5 types of nebulae: emission, reflection, supernova remnants, planetary, and dark. So here is an image of all 5 different kinds of nebulae. And as you can see, they all have their unique characteristics. So first, my research methodology. So the first step was to collect images or data. And so I got my images from the European Space Agency website, and these images were taken by the Hubble telescope. The next step was we could directly apply deep learning networks. I also decided to run a color conversion experiment where I converted the images to black and white and then ran the deep learning networks. Another possible experiment that I ran was featurization. So featurization enables us to use machine learning algorithms. The fourth step was to drop categories. This was not initially planned, but I'll be talking more about this later. The fifth step was to tune the hyperparameters, and the last step was to observe and evaluate the results. So I had many different designs to get the best model for my AI. So the first was purely deep learning. So the 3 deep learning networks I used was ResNet, MobileNet, and a custom-built net. The unique thing about the custom-built network is that it had no pre-trained model to begin with, unlike MobileNet and ResNet. And there were no other experiments ran other than hyperparameter tuning. The best accuracy was 59.68%. So that's when I decided I wanted to convert the images to black and white to see how the accuracy would be affected. So I reran the exact same thing, except I converted the images to black and white using the PIL library, also just the deep learning networks. So this chart shows the difference between the colored images and the black and white images for each deep learning network. And as you can see, there isn't much of an increase or decrease in the accuracy. So the third design was featurization and machine learning. So I ran a featurization experiment, and how this works is featurization takes a base model, in my case it was MobileNet, and it adds a global average pooling layer. But the thing that sets it apart from ResNet and MobileNet is that we don't add the softmax. So I use featurization enables us to use machine learning algorithms. And the 3 machine learning algorithms I used were random forest, MLP classifier, and k-nearest neighbors. So the result of this experiment was that it increased the overall effectiveness of the artificial intelligence. So this diagram explains how featurization works. It takes an image, and in this case, a Nebula image, and then it runs MobileNet v2 on it. So instead of converting it to the 5 categories of prediction, it's going to take the intermediate values and then use that as a feature vector for the machine learning algorithms. So this chart is able to show the difference in accuracy before and after we ran featurization, or also known as machine learning algorithms versus the deep learning networks. As you can see there, the machine learning algorithms perform better overall. The fourth design was not actually initially planned, but I was observing the confusion matrix for k nearest neighbors, and I realized the AI was random guessing for 2 categories, the reflection and dark. So I decided to drop these 2 categories to see how the accuracy would change. And although this decreased the scope of the artificial intelligence, the accuracy increased dramatically. So this was for the deep learning networks. As you can see, there's a huge increase in accuracy. And same for the machine learning algorithms. So then my 5th design was combining both the dropping categories and the featurization in machine learning. And this was the most effective as it produced the best accuracy and a satisfactory confusion matrix. I hyperparameter tuned this one as well to achieve the best possible results. So this table shows the summary of my results and my different experiments. As you can see, the maximum accuracy was 83%, and it was through MLP Classifier. So the conclusions we can reach from my research. So firstly, we can conclude that my research demonstrates it is possible to build AI models that effectively classify nebulas. Secondly, my research demonstrates the efficacy of certain techniques like featurization and the hybrid use of both deep learning and machine learning algorithms. However, there are some areas that still require some further work. So as many of you might know, the James Webb Space Telescope recently released. New images will be available soon, and they will include images of distant nebulas that will need faster classification. My research will be able to help the astronomer community identify major chemical elements in order to figure out the origins and mysteries of life in outer space. There are huge data volumes in the world of astrophysics, so my project touches on a small part of making the process of processing the data faster. So in the future, I plan to investigate the job categories thoroughly to identify why the AI was random guessing, and to try and figure out a way to incorporate these 2 categories back into my project. I actually have a hypothesis as to why these 2 categories were random guessing. It's that the images require more than just, or those categories require more than just an image to be able to classify it. They may need other factors like the light intensity of the nebula or other factors. So I will continue to add more images from the James Webb Telescope when they are available and retrain my AI to achieve a higher accuracy. Thank you for listening to my presentation, and let me know if you have any questions.
Thank you so much, Meenakshi. If you could make me the host, there are also a number of questions that I will, take you through. And you're getting some nice, messages on the chat about your presentation. So wonderful. So the first question is, how long did the experiments take to run? And in total, how much time did you spend on the experiments?
Yeah, so the experiments actually did take a while to run each one. What I did is I ran all of these in Google Colab. So I had multiple tabs open. It would take around 10 minutes or so for the deep learning networks. Those took quite a while. So running a lot of experiments did take a long time for sure.
Yeah, makes sense. And then did you use GPUs? That's another question.
Yes, I did. I had to use them to make it work.
Yeah. Mm-hmm. And then there's a question of, are nebulas the same as galaxies?
So no, they're not. Galaxies are basically the group of, I believe, a lot of astronomical bodies, and nebulas are after a star, I believe, has like, no, I don't want to say exploded. I'm not exactly sure, but yeah.
Okay, so they're not the same, basically. Okay, wonderful. Thank you so much, Meenakshi, and perfectly on time as well.